Now we are done with chapter 4 and we will start chapter 5. We will do this during this hour and the next hour. And in chapter 4, we did the first law, the conservation of energy for closed systems. And in chapter 5, we will still do the first law. There is no mention of the second law here, but we will do it in for the control volumes. Meaning, in chapter 4, the systems did not involve any mass transfer, but in chapter 5, the systems that we will deal with, they will involve mass transfer as well as heat transfer and work interactions. Okay, so what are the objectives in this chapter? Since we have mass transfer, mass entering and leaving, we need to develop an understanding of the conservation of mass, because we will have to do sometimes mass balance, okay, which is similar to energy balance, and then we will apply the first law to the open systems, control volumes. You will see the mass term there. And then we will talk about the energy transfer mechanisms, heat, work, and mass. Then we will concentrate on steady flow systems, like nozzles, compressors, turbines, throttling valves, mixing chambers, and heat exchangers. Steady flow means no changes within the device, okay, but the interactions, they are obviously different. So if let's say the operation is steady, no change with time, how do we deal with those? And most systems in engineering are that way. So we will show how to analyze those systems. And finally, what if the systems are not steady? That is, it is a control volume and not steady, meaning the conditions within the control volume may be changing with time. How do we deal with that? So these are the objectives in this chapter. And if you look at the table of contents, we simply have the conservation of mass, and then we will have to develop some understanding of flow work, that PV thing, and then energy analysis for steady flow systems, applying it to common steady flow devices, and then energy analysis of unsteady flow systems. So this is what we will do today. We will not finish it today, but next week we will also continue. Okay, so let's start with conservation of mass. This is something that you already know from not even high school, just grade school. Okay, if let's say you go to a pizza place and the pizza has like 8 slices, and if you take 5 slices, how many slices are left? 3 slices, right? Why? Conservation of mass. And okay, it is too simple. In chemistry, you always balance chemical equations based on conservation of mass. For example, if you have, let's say, 2 kilograms of hydrogen and 16 kilograms of oxygen, okay, this is what? Okay, oxygen. You get like 18 kilograms of water. That is, you have 2H plus 1O, okay, and you get H2O. Remember, it is how you balance the chemical equations there. Now, keep in mind that mass is a form of energy. Therefore, we should really have like conservation of energy and then convert the mass to energy, etc. But if you do it, you cannot get anywhere. Unless you deal with nuclear reactions, unless, let's say, you work at atomic level, okay, atomic, subatomic particles. The amount of energy in the mass is so great that when you have mass, like, 5 kilograms, and then even if you have, let's say, heat transfer, cooling, heating, whatever, chemical reactions, whatever, the energy involved is so little compared to the energy of the mass, that is energy corresponding to the mass, that you simply don't combine them. That is, you just work with mass separately, call it conservation of mass, and then work with energy interactions separately and call it conservation of energy. So in practice, these works are beautiful. If you try to combine them, you get very large numbers and very, very small numbers. You cannot add them, subtract them. You have to use like 10, 15 digits. So it is impractical. Okay, but keep in mind that mass is a form of energy, and in engineering, it is a perfectly legitimate to work with mass and energy separately. If you deal with nuclear reactions and particle physics, work with, let's say, systems that are atomic level, okay, and then you will have to combine them. But in thermodynamics, we don't have that problem. Okay, now mass flow rate. We did this in at the beginning of this course. Volume flow rate, how are they related, the velocity, etc. First of all, volume flow rate. The volume flow rate is the volume of fluid flowing through a cross section. For example, let's take this cross section here like this, okay, per unit time. That is how much volume will flow through this cross section. Okay. Now keep in mind that let's consider this region within the red dots there. Okay. Let's say the velocity, average velocity is V average. Let's say it is 2 meters per second. What does it mean? The fluid moves 2 meters per second. Okay, this is the average velocity, and we have this cross-sectional area here. Let's say this is 3 meters square, the area. Okay, so what happens here in 1 second? In 1 second, a fluid will move 2 meters, sweeping an area of 3 square meters. Therefore, sweeping a volume of 2 times 3, 6 cubic meters. And this is what we call volume flow rate. Okay, it means in every second, if you are, let's say, observing from this point, this cross section, 6 cubic meters will be passing through this section every second. So in practice, what we do is we simply say volume flow rate is the cross-sectional area times the average velocity, as we discussed before. Okay, let me use a vector there to show that it is velocity. Now, of course, this is some constant velocity. What if the velocity is not constant? Then you will have to take a small section. Let's say this is the velocity. In real life, this is the velocity distribution in a pipe. Okay, so you take a small section like this. This area right here is dA, and the velocity, the normal velocity here is this normal component. This is Vn. Okay, if you multiply these two, Vn dAc, it gives you this differential volume flow rate. Okay, and if you add them up, it will give you this entire flow rate. And if you divide it by the cross-sectional area, you will get the average velocity. So this is how you find the average velocity if the velocity is variable. In fluid mechanics, you will do that, but in thermodynamics, we will not. So here, let's say to find the volume flow rate in this case, okay, this is for the differential area, the variable velocity, and this is the differential cross-sectional area. If you integrate it, okay, you get these relations here, but this is what you need to remember from here, okay? And mass flow rate, keep in mind that mass is density times volume, right? per unit time, it is simply mass flow rate is density times volume flow rate. Okay. You can also do a differential analysis like this. That is considered a small section like this. And the most flowing through this small differential section is the velocity there times cross-section area times density. And if you take the integral over the entire cross-section, okay, it will give you the mass flow rate, the total mass flow rate, which is equivalent to you use the average velocity times cross-sectional area times density. And keep in mind that the relation between mass flow rate and volume flow rate is simply this. If you know the volume flow rate, multiply by density or divide by specific volume, same thing, you get the mass flow rate. Okay. Now, conservation of mass principle, just logic. Basically, mass in minus mass out for any system is equal to the change in mass. For example, imagine you will take a bath, okay, and during some time, 30 kilograms of water flows into the bathtub, leaves the bathtub, and through the drain out, and then 50 kilograms of water flows into the bathtub. So what is the change in the mass of water during this time period? It is 50 minus 30 is 20, right? How do we know that? Simply conservation of mass. Mass entering minus mass leaving is the change in the mass of the control volume. And just like the energy. Energy in minus energy out is the change in energy. So they are analogous. And what is the change in the mass of the control volume? The final mass minus the initial mass. Can you express it in the rate form? Yes. Divide this by delta T and take the limit as delta T goes to 0. So this is mass flow rate in minus mass flow rate out is the rate of change of the mass of the control volume. Time rate of change of the mass of the control volume. So this is the again just logic. So nothing new there. Now in fluid mechanics, you will need to go through the details of some variable cases, but I will not do it here. So you will do this in fluid mechanics, okay, in detail. But at the end, in case you have several entrances and exits, you will get a relation like this. That is the time rate of change of the mass of control volume is, you may have many inlets, the total mass entering per unit time minus the total mass leaving per unit time. Okay, so mass flow rate in minus mass flow rate out is the time rate of change of mass of the control volume. So from this page, just remember this relation here. These details I will not go through, as I said, in fluid mechanics. You will go through that. Now, steady flow process. Steady flow process, again, remember, a process during which the fluid flows through a control volume steadily, meaning no change with time. Or if you take anything, the time derivative of anything is 0 during steady processes. It may change from one place to the other. For example, the density here may be ρ1, here let's say ρ2, okay? But after let's say 1 hour, 2 hours, still there is no change here. This is constant. So is this one. This remains constant. Okay. So you may have change with location, so spatial variation, but you cannot have change with time at a specified point. So no temporal changes there. What is the result? If we have a steady flow process, then the mass of the control volume remains constant. The mass doesn't change inside, the amount of mass, and the amount of energy inside doesn't change again with time. It remains constant. Why? Because even if, let's say, the density is different, it is constant here, constant there, constant here, constant wherever, okay? And the volume doesn't change here, no change with time. So if you multiply these densities with those small volumes, add them up, they will always remain constant. Okay, same with energy. So we say under steady flow conditions, the mass and energy contents of a control volume remain constant. Okay, which means if you have a steady flow process, then dm control volume dt variation with time is 0, and the E control volume dt, okay, is again 0. That is the mass and the energy of a control volume during a steady flow process will not change. Okay. Then what is the mass balance? Now remember, the general mass balance is total mass in minus mass flow rate in per unit time minus total mass out, mass flow rate out, is equal to dm control volume dt, right? But for steady flow processes, what is this? This is 0, because m control volume is constant. So what is the result? For steady flow processes, total mass flow rate in must be equal to total mass flow rate out. We use the summation because we may have more than one inlet and or exit. But if you have a single stream, just one inlet and one exit, okay, one inlet and one exit, then M1 mass flow rate must be equal to M2, which is rho1 V1 A1, this is the velocity, must be equal to rho2 V2 A2. Okay. Let's say in this case we have like 2 inlets and 1 exit. Okay. So we have 2 kilograms per second entering, 3 kilograms per second entering. Then if the question is, what is the mass flow rate of out, how much mass is leaving? If this is a steady flow process, then we will have to add them. 2 plus 3 is 5 kilograms per second. So this is how we use the mass balance or the conservation of mass for steady flow processes. Since there is no change with time in steady flow, we always use rates. How much mass or energy per unit time. Okay. Special case, if we have a liquid incompressible flow, okay, for example, liquids, here meaning the density is constant, doesn't change during the process or the specific volume. In that case, the volume flow rates will also be equal to each other. Okay. But keep in mind that if the flow is not incompressible, like in this case, we have an air compressor. The mass flow rate is the same, 2 kilograms per second, 2 kilograms per second. Okay, but in air compressor, the air is compressed. So look at the volume flow rate. It is 1.4 at the inlet and 0.8 at the exit. Therefore, in general, this is not true, but this is true only when the density is constant. Okay, so there is no such thing as conservation of volume. It is a special case if density remains constant. Okay, a small example. Let's say this is your garden hose like this, okay, and water is flowing. How can you calculate the mass flow rate of water through that hose? Okay. Now it looks like you may think like, I have to find the velocity, the average velocity, calculate the cross-sectional area of the hose, and then multiply them. Well, it is difficult. What is the easiest way? You take a bucket like this, okay, of known volume. Let's say in this case 40 liters, okay, and measure how long it takes to fill that bucket with water. In this case, it takes 50 seconds. Okay. And obviously, what is the volume flow rate? If it takes 50 seconds to fill a 40-liter bucket, okay, then the mass flow rate of water must be 40 liters divided by 50 seconds, right? And this is the volume flow rate of water through the hose there. So just logic. It gives the diameter of the nozzle here. Okay, so we have this hose and then a nozzle. It doesn't show in the picture there. Okay, here it is what, 0.8 centimeter, the diameter, and here it is 2 centimeters right here, 2 centimeter diameter here. And the question is, what is the exit velocity? Again, using the conservation of mass principle. And okay, now we assume water is incompressible and the density is kilogram per cubic meter, which is common. And also we assume that all the water goes in. There is no splashing, okay? Volume flow rate. It looks like, okay, this is the US version of the book. Okay, so take this to be, okay, let's use these numbers. Here it says 40 liters, but change it to 10 gallons. Okay, 10 gallons. Okay, and 1 gallon is about almost 4 liters, as you see here. Okay, so just divide the total volume by the time, 50 seconds, and you get something in liter per second. This is the volume flow rate. And multiply volume flow rate by density, you get the mass flow rate. And the cross-sectional area at the exit is this one, using 0.4 centimeter there. And the volume flow rate here will remain constant because density is constant. Then what is the velocity? Divide volume flow rate by the cross-sectional area, you get the velocity. So the velocity at the exit is 15.1 meter per second. Okay. So this is how we use the mass flow rate, volume flow rate, velocities, whatever. So it was a simple and practical example. Any questions here? Okay, no question. Okay, this is more complicated. What if the velocity changes here at the exit? Okay, so you will do this problem in fluid mechanics. If you are curious, you can go through it. This is when you need to use integrations, etc., because the velocity changes there. Okay, now flow work. Now remember, we defined enthalpy as U plus PV, right? And we said that in flow systems, we often have this term a lot and this combination a lot. So we define it as enthalpy. Okay, now let's show what we mean there. Now, if let's say you are pushing a fluid with a force F like this, okay, and the pressure P, constant pressure, and this area is constant, so the force is constant. What is this force in this case? Force is equal to the pressure times the area, right? If let's say it is moving at constant speed like this, okay, then there is no acceleration, so the two will be equal to each other. And what is the flow work? Flow work. The work is force times distance, which is L. Let's say this goes through a distance L. Okay, this L here. And this force is pressure times area times L. Okay, but this cross-sectional area A times this distance is equal to this volume, as you see here. So it is P capital V. Okay, and if you divide by the mass, you get work per unit mass is P small v. And this is the work needed to maintain the flow of a unit mass of the fluid, and it is called the flow work or flow of energy. Okay, so it is the energy needed to maintain the flow of a unit mass of the fluid. Okay, as you see here, so it is called PV. And then what is the total energy? Total energy of a flowing fluid. Let's call it theta. It is E, which is the energy of stationary fluid, which is U plus kinetic energy plus potential energy, or U plus V square over 2 plus GZ. In the case of flowing fluid, let's say flowing fluid, it will be PV plus E. So PV plus U plus kinetic potential energies, but this PV plus U is H, okay? So we express the energy of a flowing fluid as H plus kinetic energy plus potential energy, okay? That is, by combining U and PV, as you see here, and defining it as enthalpy, and using enthalpy to represent the energy of a flowing fluid in control volumes, we don't have to deal with flow energy. So this is the reason we do this. Okay, it is the reason that when you have, let's say, a fluid flowing in a pipe, what is the energy here? It is H, energy of the fluid, kilojoule per kilogram. But you have a tank and you have a fluid here. What is the energy? It is U, kilojoule per kilogram. So this is the internal energy, that is the enthalpy, which combines U plus the flow energy. So this is the reason we define H, and this is what flow energy means. Okay, so we combine internal and flow energies into H, and then we don't have to deal with them separately. Okay, any questions so far? Okay, no question. So to summarize, for non-flowing fluid, okay, the total energy per unit mass is internal energy, kinetic energy, potential energy. For flowing fluid, it is flow plus internal energy plus kinetic plus potential, and we combine these two into enthalpy.
Can I ask a question?
Yes.
So, if it is not flowing, how did it have a kinetic energy?
Okay, the tank here, okay, this may be on a truck, okay. Let's say with your car, you may have it. It may be going up, potential energy, you know, accelerating, kinetic energy. That is as a bulk, the whole thing may be moving. Okay. If it is stationary, it cannot. But if it is, let's say, moving, then the potential and kinetic energy will change. Okay.
Thanks, sir.
Sure, you're welcome. Okay, so energy transport by mass. Now remember, in the energy balance, we have energy in, energy out, right? And they can be like by heat, by work, and by mass. In chapter 4, we did not have any mass crossing the system boundary, but now in chapter 5, we have mass crossing the system boundary, okay? Therefore, when mass enters a system, obviously energy enters because mass has energy. How do we account for it? Keep in mind that the energy per unit mass is theta, which is h plus v square over 2 plus gz, okay? If you have m kilogram mass entering, then how much energy is entering by mass? It is mass times m, h plus v square over 2 plus gz. Or in the rate form, let's say here you have 5 kilogram. This is what you use, 5 kilogram mass entered. Or let's say you have 5 kilogram per second mass entering. Then you have rate form, okay? So you use mass flow rate, and again, enthalpy, kinetic, potential energies. Or just logic. Often, the kinetic and potential energies are negligible, many times, not always. In that case, mass entering is, the energy entering is mass times enthalpy, or in the rate form, mass flow rate times enthalpy. If you have variable, okay, then you will have to do an integration, which we will not do much in this course. We will assume the energy is constant there. Okay. Now, let's look at energy transport by mass in a pressure cooker. In a pressure cooker. Here we have a 4-liter pressure cooker, okay, which is a common size. And the operating pressure is 150 kilopascal. It is observed that the amount of liquid in the cooker has decreased by 0.6 liters. Okay, that means instead of 4-liter water, if it is full initially, it went down by 0.6. Okay, so delta M is, delta V really is 0.6 liter. In fact, delta M will be 0.6 kilogram because 1 liter is 1 kilogram in 40 minutes. And steady operating conditions are established. That is, we start measuring after it is heated and we have steam, leaving. Okay, so inside the conditions do not change other than the amount of mass. Now, what is the mass flow rate of the steam and the exit velocity? And what is the total and flow energies of the steam per unit mass? And what is the rate at which energy leaves the cooker, pressure cooker, by the steam there? Okay, now in the pressure cooker, always saturation conditions exist. Okay, and the absolute pressure is 150 kilopascal. Okay, so what we do is we go to the steam table, to the pressure table, which is table 5, and we read the properties for liquid, the F subscript, the specific volumes, and also the internal energies. and let's say this enthalpy here. Okay, so any property we need, we can go to table 5, and at 150 we can just read them. Okay, now what is the amount of mass that left? Okay, now we know that the liquid volume inside decreased by 0.6. This is delta V, and the specific volume VF is this one, which is 0.001 and some detail there. Okay, but let's use the exact value. 0.57 kilogram. This is how much mass left. And what is the rate? 0.57 kilogram left in 40 minutes. Then how much is it per minute? Divide by 40. That many kilogram per minute. How about per second? Divide again by 60. That many kilograms per second, because 1 minute is 60 seconds, right? And what is the volume flow rate? What is the velocity? The volume flow rate is again simply you can divide that liter to 40 minutes. Okay, the velocity. Now, the amount of mass divided by rho g, okay, times cross-sectional area. Okay, the rho is the inverse of Vg, so invert it as you see. So this is the volume of the vapor leaving, and this is the cross-sectional area. So average velocity is volume flow rate divided by the cross-sectional area. Okay, it is what we did here. And we get like 34.3 meter per second. Okay, this is the average velocity. And the flow energy, it is not listed separately, but since H is U plus PV, PV is what? H minus U, right? And you can read from tables and get these values there. We never do it in practice, but this is just to understand, what flow energy is. Okay. And the total energy, okay, here let's say we have the kinetic energy, which is what, 34.3 at the exit there. And this is usually very small, the kinetic energy, as you see, 2693 versus less than 1. Okay, so usually the kinetic energy is neglected. That it is not taken into consideration, but you could also include it. Anyway, if let's say we use just the kinetic and the enthalpy dash, then the energy flow rate will be mass flow rate times the energy of the fluid. So when you multiply, you get this. If you add the kinetic energy, it will be a little different, but not much. Okay. Any questions here? So this is like how to get the properties and find velocities, flow energy, internal energy, enthalpy, whatever. Kind of to have some deeper understanding of these terms. Any questions? Okay, now energy analysis of steady flow systems. Okay, that is systems during which the mass of the system doesn't change. That is, the mass within the control volume is constant and the energy is constant. Okay, as a result, the mass in must be equal to mass out. And also energy in must be equal to energy out. Okay. So this is the steady flow of systems, and many things in practice, they are analyzed using this steady flow assumption. Okay. At least many devices, they are designed to operate steadily. Therefore, they are sized assuming steady operation, steady flow process throughout. So even though in real life, you may have fluctuations there. Okay, so the equations here, conservation of mass, okay, simply mass in, total mass in, mass flow rate in is total mass flow rate out, okay? And if you have only one inlet and one exit, okay, the mass flow rate at inlet and exit will have to be the same. So you have this, and energy balance, steady, okay, that means rate of change of the energy of the system will have to be 0. Then what do we have? Energy in must be equal to energy out per unit time. Keep in mind that energy may enter by heat, work, and mass. Okay, energy again may leave by as heat transfer, work transfer, and mass transfer. If you write it in detail, you can write it this way. If you want to write it with more detail, you can write it that way. That is heat in plus work in plus energy of the fluid in, okay, which is this is energy per unit mass, and this is mass flow rate. For you may have many inlets. So heat out, work done by the system. This is the energy per unit mass of our leaving stream times the mass flow rate of it, and then do this for each outgoing stream. So this is, I think, so what you see here is the mass balance and the energy balance. Okay. For example, if you have a water heater, an electric water heater, many of you may have it in your house. There is only one inlet, cold water in, and hot water out, assuming there is no leak. Okay, so M1 will have to be equal to M2, right? The heat loss is usually negligible, although not 0. If you assume it is 0, then the electric work input in this resistance heater here, okay, will have to be equal to the difference between the energy leaving, rate of energy leaving, and rate of energy entering. So logically, this is what we do. Okay. Okay, if you use a sign convention, you can write it this way, but no need to use that one there. Also, keep in mind that when the kinetic energy is high and you want to include it, okay, velocity is in meter per second, right? And velocity square is meter square per second square. You can show that joule per kilogram. This is same as joule per kilogram. Why? Take the joule. Joule is Newton meter, right? And Newton is kilogram meter second square, meter kilogram. And then the kilograms will cancel. What do we have? Meter square second square. So meter square per second square is same as joule per kilogram. But keep in mind it is 0.001 kilojoule per kilogram. Okay. Why this is important? Because the enthalpies are usually given in kilojoule per kilogram, the enthalpy. So if let's say you have like H plus V square over 2, okay, and this is in kilojoule per kilogram, you have to make sure that this is also in kilojoule per kilogram. which means if velocity is in meter per second, you will have to divide by 1000 at the end. Okay, so that you can add them. And also, the kinetic energy change is usually small, especially at low velocities, but at high velocities it may be significant. For example, you accelerate something from 0 to 45 meters per second, the change in kinetic energy is just 1. And usually the change in enthalpy is large. But if the velocity is 500 and it goes up to 502, a little change, instead of 45, a change of 2, see, the kinetic energy change is also 1. So at very high velocities, even if the change in velocity is small, you may need to consider the kinetic energy change there. Okay, now some steady flow devices, how these are analyzed. What we will do here is we will go through some devices like, nozzles, I don't know, diffusers, turbines, compressors, heat exchangers, whatever. So let's take a break and then continue after we come back. Okay, so I'll see you in 5-6 minutes.